Hello everyone, welcome to the series on surface tension and viscosity. I am Rahul, Assistant Professor of Physics, GVPP, Government First Aid College, Hagari. In the previous session, we have discussed about the method to determine the coefficient of viscosity given by Poiseuille's. In this session, we will discuss about the determination of coefficient of viscosity by Stokes method. Let us begin. Coefficient of viscosity by Stokes method. In the previous session, we have discussed about one of the methods to determine the coefficient of viscosity given by Poiseuille's. Here, we will discuss another very important method to determine the coefficient of viscosity given by Stokes. In this method, what we will do is we will consider a vertical long column like this as shown in the figure. Now, the liquid whose coefficient of viscosity needs to be determined is taken in this column, and we will take a steel spherical ball and we will drop it from the opening here and let the steel ball fall through the liquid and reach the bottom of this. Okay. Now, what happens is when a small steel ball which is left gently on the surface of the long vertical column of the liquid, the ball moves vertically downwards. Okay. For example, let us consider we have dropped the vertical sphere ball from here and it falls downwards. This is because of gravitational force. Let rho be the density of the steel ball. Let the steel ball that we have considered, let its density be rho, and let sigma be the density of the liquid. Okay, the liquid whose coefficient of viscosity needs to be determined, let its density be sigma. Now what happens here? The sphere will initially accelerate due to gravity. As it is falling through the column where there is no liquid, it accelerates because of acceleration due to gravity. Now once this steel ball reaches the surface of the liquid, here what happens? The viscous drag force starts to act. That is, viscous force of the liquid will try to slow down the accelerating steel ball, as well as we also have another force, that is buoyant force. We will discuss it further. Now this buoyant force will also try to keep the steel balls vertically upwards. At this point, the sphere reaches its terminal velocity. That is, as the steel ball passes through the liquid more and more, it will be accelerating due to gravity, but this acceleration will be countered by the drag force of the viscous forces of the liquid and also the buoyancy forces. Thus, by balancing these two forces, the steel ball achieves a constant speed. This constant speed is termed as terminal velocity given by v. Now what we will do is we will take the timing for the sphere to fall a known distance. That is, we will mark 2 points on the vertical column like this. Let us say this is the first mark and the second mark is like this. We will measure the distance between these two markings and we will take a stopwatch and measure the time for the steel ball once it falls from this marking to the and reaches to the second marking. The time is noted. When a sphere falls through the viscous fluid, it will experience three main forces. Consider the picture here. Now the steel ball is dropped from the top of the vertical column from here. Now at this point, the steel ball will only experience the gravity. This gravity accelerates the steel ball and makes it fall downwards. Once the steel ball hits the liquid and starts to enter the liquid, it will experience two more forces, that is the drag force and buoyancy. So the steel ball experiences totally three forces: gravity, which makes the steel ball fall; drag force, which reduces the acceleration of the steel ball as well as buoyancy, which also resists the fall of the gravity. First, we will discuss about the drag force or the viscous drag force denoted by Fd. Now, this force is the resistive force. This resists the fall of the ball. That is, once the steel ball enters the liquid has some viscosity. So this viscosity, what it does, it opposes the fall of the steel ball, because the steel ball needs to displace the amount of liquid that it is. For example, the steel ball needs to displace this amount volume of liquid to be in that place. So to oppose this displacement of the liquid, viscous forces will be acting. Now this force we call it as viscous drag force. This depends on mainly three factors. First one is radius of the ball, r. Let us imagine a smaller radius steel ball. Now if this steel ball, when it is falling through the liquid, if this is small like this must displace a very small amount of liquid. Thus it will have a small viscous drag force. But if the radius increases, now it must oppose the large amount of viscous drag to fall downwards. Thus, the viscous drag force is directly proportional to the radius r. If the r increases, viscous drag force also increases. The second factor on which the Fd depends is terminal velocity v. Now, in the previous slide, we have discussed that terminal velocity is the constant velocity that the steel ball achieves when it is flowing through the liquid like this. Okay. Now, imagine if the terminal velocity is higher. That means the viscous drag force that the steel ball must experience will be lot higher. Faster it moves, the more viscous drag it should face. Okay. The slower it moves, the less will be the drag acting on the steel ball. So again, the terminal velocity is also directly proportional to the viscous drag force. The third factor on which the viscous drag force depends is the coefficient of viscosity neta. We know that the coefficient of viscosity which the liquid has will also try to impose the drag on this falling steel ball. Higher the neta value, higher will be the viscous drag force. Thus, we can write Fd is directly proportional to R, V and neta. But however, this directly proportionality, we don't know to which power it is there. Whether Fd is directly proportional to R, or it is directly proportional to R square, or it is directly proportional to R cube, we don't know that. So what we'll do, we will take the powers as some unknowns A, B and C. So the viscous drag force is directly proportional to the some unknown power of radius, unknown power of terminal velocity and unknown power of coefficient of viscosity. If we remove the proportionality constant, we will get Fd is equals to K R to the power A, V to the power B and neta to the power C. Expressing the above equation dimensionally, we get F equals to K into R to the power A, V to the power B, neta to the power C. We know that F is equals to M into A. Therefore, mass, we have dimension of mass M, acceleration is meter per second square. So, dimensions of length and time to power minus 2. Now, the radius is measured in length. So, length dimension of length L to the power 1 to the power A we have taken here. Here, the constant velocity or the terminal velocity V is given by meter per second. Therefore, length into t to the power minus 1 B taken here. Now, the coefficient of viscosity, we know that its SI unit is kg per meter per second. So, kg is mass to the power 1 per meter L to the power minus 1 and per second, that is t to the power minus 1 into C taken here. Now we know that the powers can be multiplied inside. So this becomes L to the power A, L to the power B, T to the power minus B. This M to the power C, L to the power minus C, T to the power minus C. Now adding whose bases are same, we get M to the power only one is there here, say that is m to the power c. Then for L we have n to the power L to the power a, L to the power b and L to the power minus c. Therefore this becomes L to the power a plus b minus c. And for time dimension, t to the power minus b, t to the power minus c. So this becomes t to the power minus b minus c. Now forces of dimension of force is taken here. Now these, for both sides the powers of the dimensions must be equal. Therefore equating the powers on these two equations we get C, which is here mass power C. Here the mass is 1, so we get C as 1. Okay. Then equating the powers of length, we have L to the power 1. Now this must be equal to A plus B minus C. Then T is minus B minus C. Now we should be equals to T to the power minus 2. So minus 2. Solving these three equations, that is substitute this C in here, we get B equals to C is 1, we all know that. Then when you substitute C value here, you get B is equals to 1. Now substitute B and 1 in this this equation, we get A equal to 1. So now we know the dimensions of the each values. Substitute these values in equation 1, we get the drag force or the viscous drag force Fd is equals to constant into r to the power 1, v to the power 1, eta to the power 1. Now this is given by Stokes law. Okay, Stokes law states that the viscous drag force Fd acting on a sphere of radius r moving with the steady velocity v through a fluid of viscosity neta is given by Fd equals to 6 pi r v into neta. This is the Stokes law. Understood? Stokes law is it gives the relation between the drag force and the factors on which it depends, which is Fd equals to 6 pi into r v neta. Now here you can observe that 6 pi is nothing but it is the constant value k. Now this was calculated by Navier-Stokes equation, which you will study in higher classes. So finally we can conclude that the steel ball which is falling through the liquid whose viscosity needs to be determined, that the viscous drag force is given by Fd is equals to 6 pi r v neta. Take this as equation 2. The second type of force which is acting on the steel balls is the buoyant force. Buoyant force is the upward force exerted by a fluid on an object that is partially or fully submerged in it. For example, consider a boat. Why does a boat float on the liquid? Because the buoyant force is responsible for that. This buoyant force, what it does, it pushes the boat upward, which is submerged, partially or fully submerged in it. That boat will be pushed upward by this buoyant forces. Okay. Now this force acts opposite to the direction of the gravity, and it is responsible for making the objects feel lighter in water. That is, if you hold any material which is heavy in water, it feels lighter when you compare the weight of that when you are holding that material outside. So that's because of the buoyant forces. What it does, it pushes the partially submerged or fully submerged objects upwards against the gravity. Now this buoyant force is given by Fb, okay, which is equals to volume into density of the object that is floating, rho, into gravitational force. This gives the buoyant force. Understood? See, buoyant force which is acting on the steel sphere ball is equals to 4 by 3 pi r cube rho into g. Take this as equation 3. Now finally the third force acting on the steel ball is the gravitational force, which pulls the steel ball downwards. Nothing but the weight of the ball. Okay, we know that the gravitational force F equals to is m into g. Now mass, we know that it is volume into density. Volume of the steel ball is 4 by 3 pi r cube. Then density is rho multiplied by gravitational g. So this gives us the gravitational force Fg, mg. Now in equilibrium, all the three forces will be stable. That is, the upward forces like viscous drag force and buoyant force, and downward force, gravitational force, these will be equal. That is nothing but the upward force acting on the ball must be equal to the net downward force acting on the ball. Upward force is the viscous drag force 6 pi r v neta plus buoyant force is 4 by 3 pi r cube rho g. We should be equal to downward force, which is the gravity, 4 by 3 pi r cube rho g. On simplifying, we get 6 pi r v neta equals to 4 by 3 pi r cube into rho minus sigma into g. R, 1 R get cancels, V 6 pi comes down here. So finally we get neta as 2 R square rho minus sigma into G whole divided by 9 V, where R is the radius of the steel ball, rho is the density of the steel ball, sigma is the density of the liquid taken, and g is the acceleration due to gravity. V can be experimentally measured by measuring the time taken for this steel drop to travel a specified measured distance through the liquid. Thus, we can calculate the value of coefficient of viscosity by Stokes method. So that concludes chapter 5, surface tension and viscosity. Thank you.